In this video, we're going to be using the turns ratio that we can determine using the voltage here instead of turns. We don't have the turns that we've had in other videos, but we have the voltage here to determine what the current is through each winding. And it doesn't matter if we're talking about the secondary winding or the primary winding. So the first thing we're going to do when we get started is we're going to determine what the turns ratio is, and we do that by taking 1200 volts divided by 240 volts to get our turns ratio. Again, it is always the higher number divided by the lower number to get the turns ratio. In this case, it's a 5-to-1 ratio. Next up, what we're going to do is we're going to assign a voltage at the source here. So it is rated 1200 volts to 240, but that doesn't necessarily mean that we're putting 1200. It just means that the maximum voltage that we can handle here is 1200 volts. In this instance, however, we will add 1200 volts to the source. So we have 1200 volts at the source with a 5-to-1 ratio. 1200 divided by 5 will give me the secondary voltage here, which in this case is 240 volts. Next up, we'll be adding a resistance. So in this case, I'm just going to assign the resistance to be 16 ohms. So we can determine the secondary current at this point by taking 240 volts divided by 16 ohms to get my secondary current, which in this case is going to be 15 amps. Now, this is where we can start using the turns ratio. So we have 15 amps on the secondary, and we have 240 volts on the secondary. We have 1200 amps on the primary. We need to remember that lower voltage means higher current, higher voltage means lower current. So when we use this turns ratio, we've got the higher current here. We're going to go 15 amps divided by 5 to get our primary current, which in this case works out to be 3 amps. So that's using the turns ratio. Now, I find that using the turns ratio for current can be a bit confusing sometimes because we get so used to stepping the voltage down that we forget sometimes that we have to take the current, and if we've got a higher voltage here, we end up with a lower current. So that can get a little confusing when we're using ratios. The way I like to work out these is taking that extra step and using the idea that our VA in is equal to our VA out. And what I mean by that is the power that this side uses is the power that this side has to give. So if I have 240 volts here with 15 amps, I can determine the power by taking 240 times 15 amps to get the power that this side is using, and whatever the power this side uses, this side has to give. So that is the idea of VA in equals VA out. VA in equals VA out. It's one of the primary rules of transformers. Along with the volts per turns primary equals volts per turns secondary, whatever the output of the power is of the transformer is got to equal the input of the power of the transformer. So going back to our original example, 240 volts divided by 16 ohms, gives us 15 amps. 240 volts times 15 amps will give us 3600 VA. If we have 3600 VA on the secondary, that means we have to have 3600 VA on the primary. And now that we've determined that we have 3600 VA on the primary, we can take 3600 VA divided by 1200 volts and get our primary current. In this case, that equals 3 amps, which is what we worked out before when we used the turns ratio. I know it seems like there's an extra step involved, but I just find it way easier to deal with the VA in, VA out rule than trying to remember that I might have to step up or step down my current depending if it's a step up or step down transformer. So again, VA in equals VA out will get you the right answer all of the time, and you don't have to confuse yourself so much with the turns ratio and the current. In this video, we're going to discuss how to calculate the percent impedance of a transformer using what is called the short circuit test. Now, in my 20 years in the trade, I've never actually done this test out in the field. I've done it as a teacher in a classroom. So it's something that's not very practical, but it is a good example of how we come up with that number for percent impedance. And percent impedance is very important to us as electricians because that's what determines how we parallel our transformers. Remember, the 3 rules for paralleling are that you have to have the same voltage rating, you have to have this observed same polarities, and you have to have the same percent impedance. So we're going to show how that's calculated, use what's called the short circuit test. Now, a good place to start with anything especially when you're dealing with transformers, is to work out ratings. Now, I've given you the rating here. I've told you that this transformer here is a 4160 volt to 120, meaning the high side sees 4160, or you can see a maximum of 4160 volts. The low side will see 120 volts, and it's rated at 20 kVA, which means that each winding here can handle 20 kVA. So we're going to use 20 kVA, divide that by 4160 volts to determine that we have a maximum rated current of 4.8 amps that can run safely through the winding here. Anything over that, and you risk burning out the windings. This next calculation isn't necessarily necessary, but just to make the point that when we have 4.8 amps running in the primary side here, so if we have maximum current flowing in the primary side, we are also going to have maximum current running through the secondary side. Very important, because we have what's called a shunt bar here. Your shunt bar needs to be able to handle that maximum current, because we will be taking this guy up to its maximum current on the primary, which does mean that you will see 167 amps on the secondary. So it's just something that you need to be aware of. All right, so what we're doing now is we're taking this AC supply and we're going to very slowly start cranking it up. So we're going to start increasing our voltage until our ammeter that we have connected here in series is reading 4.8 amps. So slowly raise this voltage up until we read 4.8 amps. Then you notice we've got a voltmeter across the winding here. We're going to take that voltmeter and read what voltage it takes to impress 4.8 amps on this side. Now, it's not going to take very much voltage. I know 104 volts is not very much, considering that it can see 4160 volts, but keep in mind it has a short circuit here, and from previous videos we've learned that the secondary side is what controls the primary's current. So there's very little resistance on this side, which therefore means that this current's going to go up, which is going to increase that current as well. So I'm telling you that, and this is a number that your voltmeter will give you, or I'm going to tell you in this video, that as we cranked it up to 4.8 amps, that your voltmeter here is reading 104 volts. There's no calculation for that. It's just a reading that you will get. And now comes time to use the formula for percent impedance. We have the formula here. E short circuit divided by E rated equals percent impedance. Our short circuit voltage is this, the 104 volts that it took in a short circuit condition to reach rated current. 104 volts. Our rated voltage is 4160 volts. So we're going to take 104 and divide it by 4160. 104 volts divided by 4,160 volts gives us our percent impedance of 2.5%. So now we have all the ratings for the transformer. We have the kVA rating, we have the voltage ratings, and we have the percent impedance ratings. This percent impedance will become very important in another video where we use it to determine what the fault current available to the transformer is based off of the percent impedance. In this video, we're going to be discussing paralleling single winding transformers. Now remember, when it comes to paralleling transformers, there's 3 rules that have to be obeyed. Number 1, you have to have the same voltage ratings of the transformer, and that has been covered in another video. Secondly, you have to observe the instantaneous polarity. Now that is not to say that they both have to be subtractive or both have to be additive, but that's what we'll discuss in this video. And thirdly, they have to have the same percent impedance. So let's go ahead and start talking about how we are going to parallel a subtractive polarity transformer with an additive polarity transformer. It seems like it can't be done. Oh, but it can. Now, when we go ahead and we are paralleling the transformers, the first thing we do is we basically stop time and we pick a polarity. So what we're going to do is we pick the line polarity here. I've picked the top as being negative, the bottom as being positive. That doesn't matter. You can go ahead if you want and pick the top as positive, bottom as negative. It seriously doesn't matter. It's all going to follow through all the way down to the secondary bus. So right now for this example, again, negative on the top, positive on the bottom. Now, when you pick the line polarity ends up determining the primary winding's polarity. So we see here that we have a negative line. Here it goes down. That's going to make H2 negative and H1 positive because that's hooked up to the positive line. Same thing down here for the second one. I've got H1 is positive, H2 is negative because the H2 is hooked to the negative line, H1 is hooked to the positive line. So again, you pick the line polarity determines your primary polarity, and then your primary polarity determines what your secondary polarity is. So here we go. Remember that with the rule of transformers, H1 and X1 are always going to be the same polarity. So here we've got H1 is positive, so X1 is going to be positive, which means that if H2 is negative, X2 is negative. Over here, I've got H1 is positive, which means that X1 over here is positive. So watch out for that, because over here it was across the way. Over here, X1 is positive, H2 is negative, X2 is negative. So again, you pick the line polarity. The line polarity determines the primary polarity, and the primary polarity determines the secondary polarity. And then from there, that determines what your secondary bus is. So I'm just going to go ahead and I'm going to use this transform as my reference. Now, you see here I've got X1 is positive and it is connected to this line here. That makes this line positive. This is X2 is negative. It's connected down here. That makes this negative. So what I have to do now is make sure that this transformer's windings are connected the same way. You want the negative lines to be touching and you want the positive lines to be touching, or else you get Kablazelflam. So we have here negative X2 is down here. It is on the negative line. We're all good. And X1 is on the positive, which is here, which is connected to the positive line, and we're all good. That falls through as long as you got your polarities matched up. It doesn't matter if these windings are all swapped out, as long as by the time you get down here, you've got a positive line, which all the terminals that are positive are connected to, and a negative line, which all the negative lines are connected to. You are good to go.